Good morning, class 10s. Pay attention, please. We will be getting back to those stoichiometry chapters again. We'll be doing empirical formula and all that when the school reopens, and we'll be doing the other sums also, numericals that are there in chemistry. Okay, but for the time being, now it's difficult to do all that in online, so let us get into this. Okay, and I hope to finish this between two lessons. Right, now this is the study of compounds. Hydrogen chloride. Now you know all about hydrogen chloride, chlorine third orbit, having 7 electrons. Okay, hydrogen the very first orbit having 1 electron, and therefore okay, they share the electron over here. Chlorine becomes 8, hydrogen becomes 2, hydrogen becomes duplet, chlorine becomes octet. They share the electrons, and therefore hydrogen chloride is a covalent compound, and we know from that chemical bonding and all that chapters that it is also a polar covalent compound. Okay, hydrogen chloride is a polar covalent compound. Fine. Right, Glober prepared the acid by heating NaCl with concentrated sulfuric acid, and Lavoisier named it muriatic acid. Hydrogen chloride gas occurs free in state. Fine, that's okay. General preparation of hydrogen by synthesis. Synthesis is direct addition method. We have it over here. Hydrogen plus chlorine reacts to give you 2HCl. In diffuse sunlight the reaction is slightly controlled, but in direct sunlight, the sunlight that you have in your home right now with the windows and the doors open, that is diffuse sunlight. Okay, there the reaction can be controlled, but in direct sunlight it is very explosive, and in no sunlight there is no reaction. How is it done? Okay, by burning a jet of hydrogen, okay, in chlorine gas. Fine, that's the synthesis process. Then we go on to the heating of metallic chlorides with concentrated sulfuric acid. Mind you, the background of this reaction is the more volatile displaces the less volatile. Okay, HCl is highly volatile compared to sulfuric acid, so HCl is more volatile, so it displaces the less volatile. I cannot have the reaction the other way about. With the help of HCl I cannot get sulfuric acid. Got it? This is the background of this reaction. More volatile, HCl is more volatile. We'll be talking about its volatility. Okay, more volatile displaces the less volatile. Am I clear there? Below 200, sodium bisulfate. Above 200, sodium sulfate. We'll see to that. The lab preparation. Okay. Alright, because the lab preparation, we are doing the same thing. We are using sodium chloride and concentrated sulfuric acid. Okay, we have sodium chloride there. Through the Thissell funnel we get the concentrated sulfuric acid, and the gas is passed through sulfuric acid to dry the thing. Is it okay? And finally it is collected by the upward displacement of air. Reason is because it is 1.28 times heavier than air. It is heavier than air, therefore it is collected by the upward displacement of air. Got it? So the reaction is over here. We have the reaction over here. Okay, less than 200 degrees C we get bisulfate. Right, if it is more than above, look at this, if it is above 200 degrees C we get sodium sulfate. We don't go above 200 degrees C. You have the point over here. We don't go above, somewhere it is over here. Okay, anyway, we don't go above 200 degrees C because unnecessary we are wasting energy. Okay, and sodium sulfate forms a hard crust which will stick to glass, and it spoils the glass. Therefore we maintain a temperature of below 200 degrees C. That's all for this. Okay, why do we use sodium chloride? Because sodium chloride, you know, is common salt. It's very cheap. Sodium chloride is very cheap to be used. Okay, and the nitric acid is not, we don't use nitric acid, mind you, because nitric acid is also volatile. Okay, so it will volatilize with HCl. So the HCl gas coming out will be contaminated with nitric acid. On the other hand, we are safe with concentrated sulfuric acid, because concentrated sulfuric acid does not volatilize. I mean, it is very less volatile compared to HCl. Did you get that? Okay, purification of the gas. We purified, as you said, we purify it with the help of concentrated sulfuric acid. Then why don't we use, look at this, why don't we use phosphorus pentaoxide or quicklime? With phosphorus pentaoxide, HCl gives you, okay, this is the reaction for phosphorus pentaoxide. And with calcium oxide, of course, with calcium oxide we cannot do, because calcium oxide is a base, it's a basic oxide. So acid plus base will give you salt plus water, right? Remember, we never, it's a rule, we never dry an acidic gas with the help of basic salt, and a basic gas with the help of acid salt, with the help of acid. Okay, did you get that? Sulfuric acid is a good drying agent. I think we have done that, somehow we'll be doing it. Okay, it's a good drying agent and dehydrating agent. Okay, so HCl can be dried with that. All right. Okay, why do we collected the thing? As I told you, it is 1.28 times heavier than air, and it is not collected over water because it is highly soluble in water. Highly soluble in water. Therefore, it is never collected over water. We will be talking about that part. How do I identify the gas? The jar, when the thing is gas is being produced, the jar is completely filled with chloride fumes and so on, whatever it is. When hydrogen chloride gas is exposed to air, now this question is asked. HCl gas is colorless. HCl gas is colorless. You'll have it in the laboratory also, sometimes we can check it out. When HCl gas is colorless, but when you open a concentrated HCl bottle, you'll find white fumes coming out. Why? HCl gas is colorless, but when you open an HCl bottle, you'll find white fumes coming out. Reason? Number one reason is because HCl is highly volatile. So the moment you open it, you find the vapors coming out. And because HCl is highly soluble in water, it dissolves in the moisture of the water, forming droplets of HCl acid. So there are 2 points. Number one, it volatilizes, okay, very fast, and then HCl gas dissolves in the moisture of the water, forming, because it's highly soluble in water, dissolves in the moisture of the water, forming droplets of HCl acid, which you see it as fumes. Those fumes are not actually smoke, they are droplets of HCl acid. No, that's a question all by itself. Okay, so that's it. And then another way that we think, I think we have done that in chemistry, practical. Okay, HCl gas. Okay, if you take a rod dipped in ammonium hydroxide, you get dense white fumes of ammonium chloride. So two gases, no, HCl gas combines with, that is, I was thinking about ammonia, same thing happens in the case of ammonia, but over here we take ammonium hydroxide solution, dip the rod in HCl, dip the rod in ammonium hydroxide and put it on the mouth of HCl gas, you will find, okay, fumes of ammonium chloride. Is that okay? Right, we have done this for our practical, we have done that. Did you get that, everybody? Okay. All right. Yeah, 9 minutes. Fine. All right. Look at this precaution. What is the precaution that we should be taking? Lower end of the sessional funnel should be dipped inside concentrated sulfuric acid. Delivery tube should be dipped in drying agent. Temperature should be maintained so and so, nearly 200 degrees C. At higher temperatures, right? At higher temperatures above 200 degrees C, the apparatus, which is made of a glass, might crack. The fuel is wasted, and as I said, sodium sulfate that is forms a hard crust and sticks to glass. Okay, right. The physical properties: color, colorless, pungent, choking smell, acidic, fine. Physiological nature, it's corrosive in nature, irritates your nose, throat, fine, go through all that. Okay, vapor density HCl 18.25, that of air is 14.4. okay, it is, as I said, 1.28 times heavier than air. Boiling point, melting point, liquefaction. When subjected to high pressure at low temperature, it is liquefied to a colorless liquid. Solubility, highly soluble in water. Okay, remember that point, highly soluble in water. Okay, that needs to be explained a little bit. Look at this experiment. Yeah, look at this experiment. Look at this experiment. Okay, this is an experiment to show that, okay, HCl is heavier than air. You can literally pour the HCl gas into a jar like that. So you have a candle burning over there. Now that is burning because of oxygen, air. So when you pour that HCl gas, just tilt that jar on it, it will displace the air and the candle will extinguish. It shows that HCl is heavier than air. Is that okay? Now this needs to be explained. Okay, pay attention to this. Look at this fountain experiment. Okay, and you have a similar experiment over here. In the case of ammonia, you will find another experiment over here. For ammonia, same thing. See, look at this ammonia, same type of diagram, I mean same type of apparatus. Okay, the same principle is applied over here. So what are we trying to prove over here? The idea behind this experiment is to prove that HCl is highly soluble in water. So what we do is we take blue litmus solution over here. Okay, there is a dropper there which is having water in it, a dropper with water, and there is HCl gas over here. Here you have the HCl gas, round bottom flask full of HCl gas. Did you get that? Okay, so what you do is you press the dropper and you push in some water into this cylinder. The moment you push in some water into the cylinder, HCl, being highly soluble in water, dissolves in that water. HCl, being highly soluble in water, dissolves in the water, forming a partial vacuum over here, forming a partial vacuum over there. And because of that partial vacuum, the blue litmus over here runs up to fill up that space. And when the blue litmus runs up, it ends up in a red fountain. Why? Because the blue litmus comes in contact with HCl acid. Okay, and you know, blue, in presence of acid, blue litmus turns red. Did you get the idea? Okay, so the blue litmus runs up. You can see the blue litmus running up, but ending up in a red fountain like a magic. So that's what's the idea behind it. It shows that HCl is highly soluble in water. Okay, right? We have the dropper over there. Press the dropper, push in some water into that cylinder, round bottom cylinder thing, flask, and then because HCl is highly soluble in water, okay, it dissolves. The HCl gas dissolves in that acid, forming a partial vacuum. Because of that vacuum, the blue litmus runs up, ending up in a red fountain. Did you get that? In the case of ammonia, you will find same thing. Over here you have red solution, red litmus, ammonia gas, red litmus running up, becoming blue. Why? Because ammonia is an alkaline gas. Reason, ammonia is also highly soluble in water. Did you get that, everybody? Is that clear? Clear that much? We'll stop over here for the time being, and tomorrow we carry on from here, and hopefully we'll see. You'll find this over here. Just look at this, please. Remember that chart that I gave you people in class 9? Remember the chart that I gave you people in class 9? See, same thing. Metallic oxide with an acid, salt and water. Metallic hydroxide with an acid, salt and water. Okay, all carbonates, and bicarbonates with an acid, salt water, carbon dioxide, all sulfides and bisulfides with an acid, salt water, sulfur dioxide. So all these are common equations which you will find in, because we have three acids over here, HCl, H2SO4 and nitric acid, the same stereotype of equations you will find. Okay, so if you go back to those charts, you will find all the things have been mentioned over there. All these equations are mentioned over there. Got it? This metallic oxide is a basic oxide with an acid, salt and water. Metallic hydroxide is a complete base with an acid, salt and water. All carbonates, bicarbonates, all sulfides, bisulfides, everything. Is that okay? So I would suggest you to go back and have a look at that, and these chapters will become very, very easy. Okay, that's all for today. I'll be sending another lesson tomorrow. Okay, I'll finish off this for the timing and we'll stop. Then when the school opens, we'll see. Right? Thank you everybody. Have a nice day. God bless.